Okay, so welcome to the first session of the last day of Eurocrypt. I'm the chair, I'm Dennis Hofheinz, and this talk is going to be about, or this session is going to be about pseudo-random functions, and two of the talks are going to have application in the title, and according to Serge and Pierre-Alain, that seemed to be a feat to get those in, so I'm looking forward to very strong talks in this session. The first talk is going to be given by Bo Peng, and it's on pseudo-random functions with weak programming privacy and applications to peer. So, Bo, the stage is yours.
All right. Is this mic working? I guess. Okay. Okay. Thanks for the introduction. I'm Bo Peng from Peking University. I'm going to talk about PRF with weak programming privacy and applications to private information retrieval. So this is joint work with Arishjit, Mingxun, and Elaine from Carnegie Mellon University. Okay, I guess this thing isn't working. No. Okay. Okay, so first, what is information retrieval? Imagine there's a server that has a public database, and the user can ask the server about this database. So you can ask, what is the location of Eurocrypt 25? And the server will tell you it is in Madrid, Spain. But this query leaks user privacy because if the server is malicious, then it can know that you are probably a cryptographer. And private information retrieval wants to solve this problem by encoding the query and the response, such that even if the server wants to learn something about you, it cannot. Okay, and recently there are many advances on preprocessing PIR, which is a specific type of PIR, and many of them follow a common framework, which I will introduce next. So in preprocessing PIR, it is separated into two phases, the preprocessing phase and the query phase. And we model the database on the server as a vector of length n. And in this framework, during the preprocessing phase, the user is going to download the entire database and preprocess it into a local hint. Now in this framework, the local hint consists of square root n sets. For example, there are 3 sets here. And each set is represented by a PRF key. So the PRF key expands into the elements of the set. And each of the sets contains square root n random elements. And in addition to the sets, the user is also going to store the sum of each element in the sets. For example, when the set is 257, the user is going to store db2 plus db5 plus db7. Now during the online phase, the user wants to ask, what is db2? Right, so it looks into its local hint. It finds a set that contains 2, so it has db2 plus db5 plus db7. And it also grabs a random entry, which is also stored during preprocessing, which is db1. Now it takes the 2 from the set, so it's 257, it removes the 2, and it adds in the 1. And it sends 157 to the server. Now the server replies with db1 plus db5 plus db7, and as you can probably see, this already gives you db2 by some addition and subtraction. Now, you may find out that sending 157, it uses very large communication because this is a set of size square root n. All right, so we want to address this communication bottleneck. We want to send the set in a succinct manner. We don't want to send it like in the way of square root n elements. And how do we do it? Recall that 157 is obtained by 257 minus 2 and plus 1. And the 257 is obtained from a PRF key. So now we want to transform a PRF key MSK into another key PSK such that they satisfy their evaluation differ at exactly 1 position. So this allows us to remove the 2 and add 1. And also PSK leaks no information about the different position. We don't want it to leak which position is differing. And finally, we want to minimize PSK to minimize the communication. And if you are familiar with this notion, it is quite similar to a private programmable PRF or PVPRF. So if we construct a PVPRF with small key size, then we can address this bottleneck. Now, let's start with puncturable PRF or PPRF. It is quite similar to a PRF. It has the evaluation algorithm eval. And for any y, you can puncture it, generate a puncture key PSKY from MSK. And it goes with the puncture evaluation algorithm. And for correctness, we want that their evaluation is almost the same except on the punctured position. And for security, we want that given PSKY, the original evaluation is indistinguishable from random. So it hides the original evaluation. And this is very simple. It can be constructed using the classical GGM PRF. Now, what about privacy and programmability? Ordinarily, a puncture key PSKY, it reveals y, as it is in the case of GGM PRF. So for privacy, we want it to not leak anything about y, it hides the punctured position. And for programmability, we want to program PSKY such that it outputs a desired value at y instead of a random value. And it has many applications, watermarking PRF, MPC, and PIR, which I just talked about. Now, how do we construct a PVPRF? There are some previous constructions which are based on LWE or IO. But for example, the LWE constructions are similar to layered FHE, so they are quite slow. And LWE or IO are strong assumptions. There's also another previous construction that is based on one-way function, which is BJIK22. But it comes with the drawback that the evaluation time is omega n, where n is the domain size. So even with small domain size, the evaluation time is quite slow. Now we ask, can we construct a PVPRF based on one-way function with efficient evaluation? So let's first put forward a strawman. We have a baseline BJIK22, which has evaluation time linear in the domain size. So it's natural to think maybe we can make the domain size smaller, right? So we can divide the domain size n into square root n blocks. And for each block, we assign a BJIK22 key. And during evaluation or programming, we only need to expand a single key, which has domain size only square root n. Right, so it works as follows. The MSK contains square root n subkeys. Each subkey is a BJIK22 key. And each of them evaluates two separate domains. And suppose we want to program F2, then we just program MSK0 and leave the other keys unchanged. Right, so we have square root n key size and square root n evaluation and program time. This is already much faster. But what about privacy? As you might already notice, it does not satisfy privacy because we can easily identify which block was programmed. And therefore, we put forward a generic solution, which is flooding. Instead of assigning each block only one key, we will assign them polylambda keys. And each of them might be normal, or they might already be programmed. And during programming, we will only program one of the normal keys, such that after programming, each of the blocks still contain many programmed keys and normal keys. So the adversary cannot tell which block has one more programmed key due to my program. Right, so it works as this. Now there are 3 keys inside each block, and we will XOR their evaluation together. And for example, we want to program F2, then we select a random normal key in the first block, and we program it. So it suffices to program a single key to make it output W at F2. And now you might see that the first block and the second block, they have the same number of normal keys. So intuitively, the adversary cannot tell you programmed block 1 or block 2. Now, this cannot guarantee full privacy because some of the information is still leaked by the number of normal keys. But it achieves a notion of weak PVPRF, which we define as the adversary cannot distinguish PSKY from PSK0 with probability inverse polynomial. You can see this as a relaxation of statistical distance. And intuitively, PSKY leaks Y with probability at most 1 over poly lambda. Okay, so now the strawman has 1 over poly lambda privacy. And now the key size is still not poly lambda, so we want to reduce key size now. And here's the crucial observation. We only touched or used constant keys during evaluation and programming. So we only changed constant keys during programming. And the idea is you can use a PVPRF to generate those keys instead of sending them in the clear. Right, so now we can use recursion to reduce the key size. We only use one key, a BJK22 key, MSK, and we use top-down evaluation. In the level 1, we will expand MSK into square root n BJK22 keys. And in level 2, each of the keys expand into square root n pseudo-random values. So it's quite similar to a GGM PRF, but we are using a BJK22 key, so we can support large fan-out, square root n fan-out. All right, so it works like this. We have an MSK. The MSK expands into square root n keys, and each of them evaluates into their own domain. And for programming, we use bottom-up programming. So we first program the level 2 key to let it output the desired value at the programming position. And then we program MSK to output the programmed level 2 key. So like this. If we want to program F2, then we will first program MSK0, program it into PSK0 such that it outputs W, and then we program MSK such that it outputs PSK0. Okay, so now we have poly lambda key size and square root n evaluation and programming. So it's quite good. But what about privacy? As you might already noticed, it has the same problem because the adversary can easily identify which path was programmed. And again, we will use flooding. We will use, instead of one, we will use poly lambda MSKs and only program one of them. So you can imagine the trees are no longer abnormal. There are some programmed keys inside. And we will find one MSK that the path is all normal, and we will program the path. So you can see our paper for details. But anyway, it's just flooding. And can we do better than square root n? Turns out we can, because now we are only a 2-level tree, but we can go all the way to 10 levels, and there won't be any fundamental difference. Right, so now our key size is still poly lambda, but evaluation or programming is only n to the 1/10, because now the fan out is only n to the 1/10, and yeah. And it's natural to ask, can we take it all the way to log n levels? But unfortunately, no, because our key size blows up exponentially on the number of levels. So we can only do constant levels. Okay, to summarize, now we construct a PVPRF, assuming only one-way function. And for arbitrary constant epsilon, we have a PVPRF with key size lambda to the 1 over epsilon, and our evaluation and programming time is only n to the epsilon. And this comes with 1 over poly lambda security. Now, another problem is that as a cryptographer, you might ask, why would anyone care about 1 over poly lambda security? But we borrow another technique from BJK22, which is called security amplification. And this technique can help to boost our security into negligible. Due to some problems, we cannot quite apply their technique to our PVPRF. But when we use our PVPRF in the PIR, we obtain a weak security PIR, and then we apply security amplification to the PIR, such that we obtain negligible security in PIR, and it comes with very small runtime overhead. Right, and to summarize, using our PVPRF in preprocessing PIR, we get poly-lambda online communication, whereas the previous best solution needs n to the 1/4 communication. And for offline communication and computation, which are just another two matrices, we do slightly worse, but not too much worse. Right. And for some future directions, our PVPRF is based on one-way function, but it is definitely not practical. So we want to ask if we can build concretely efficient PVPRF, maybe based on stronger assumptions such as LWE. And maybe this very strong technique of security amplification can have more applications, which I remember there's a talk a few days before that also uses this application. And maybe we can build more primitives based on one-way functions, such as the PVPRF. And you can read our paper on ePrint, and this is all we have. Thank you.
Thank you very much for the talk. Any questions?
Hi, thank you for the talk. When you compare with the prior work, there's a lot hidden in the O lambda. So are the polynomials in lambda comparable with the prior work, or is it very different?
Is it comparing with PIR or PVPRF?
The PIR result.
Oh, PIR.
Like when you go to constant from square root n in the online communication, if I were to spell out the polynomial in lambda, is there something that can still be improved there, or are they comparable, or is it?
Well, I guess, for example, you can take epsilon to be like 1/6. So now our online communication is a concrete polynomial, maybe lambda to the 12th. But it does not depend on n, so we can take n to lambda to the 100, and we will be better than prior works.
I see. Thanks.
Thank you.
Any other questions? So maybe I have a quick question. So you only achieve 1/poly of lambda security. Do you have any ideas or indications whether you can get to full security, to negligible security for the PRF itself?
Sorry, you mean are there other applications for this poly security PVPRF?
No. I understand there are applications for this 1/poly security, but you can boost the application. You can boost the security in the applications. Can you also boost the security of the original construction?
Okay, so in the BGIK22 construction, they boosted the PVPRF security, but it comes at the cost that the evaluation is now inherent to be polynomial time in the domain size. And we did a lot of work to avoid this long evaluation time, so we cannot quite apply this technique to our PVPRF. Because if we apply, then our work is like all lost.
Okay.
Thank you.
Okay, if there are no more questions, then let's thank Bo again. And the second talk of the session is about distributed randomness using weighted, verifiably unpredictable functions. And the talk will be given by Sodaf Das.
Okay. Hi, everyone. I'm Saurav. I'll talk about our paper, Distributed Randomness with Weighted VRF. This is a joint work with Benny, Aline, who is also here, and Jolun. And before I start, I want to say this is, I'll talk about part of the cryptography that powers the randomness beacon in Aptos blockchain, and it has been running in production since March 2024, and it has received more than, I think, millions of transaction calls. Okay, let's start with the high-level problem definition. So our goal is to design a randomness beacon, which is, you can think of this ideal functionality which has a clock inside it, and it periodically outputs random values. It outputs a random value R1, and after a while it will output another random value, and so on and so forth. So this is the ideal functionality we somehow want to implement, and it has many applications. In general, randomized jury, consensus protocols, clinical trials, digital lotteries, drafting, these are normal applications of randomness beacon. But in blockchains, also we have a lot of applications of randomness, like this maximum extractable value protection, leader election, games and lotteries that happened a lot, NFT minting and airdrops, possibly many more. So we want to design randomness for blockchains, and one approach to do that is to rely on an external coin oracle, and this is how it will work. So external coin oracle is just external source of verifiable randomness. So let's say, and there are some examples such as DRAND and Chainlink. Let's say we have a blockchain that wants to use randomness beacon, and we have an external oracle DRAND. Then after we generate each block, the validators can query this external oracle to get a random value and use that in their blockchain, and can do it again and again. But it has a few limitations. It has the security limitation that now blockchain will implicitly rely on the security of the external randomness beacon, which is undesirable in many applications, and also it has a usability issue that it's hard to get the timing right. So if you query for a random value and it didn't arrive yet, you have to stall the execution of the transactions and so forth. And there's another third reason is that this external VRF will cost you. This also becomes expensive for application development. So we don't want to do that. Instead, we want to design a protocol where the blockchain validators themselves are running the coin protocol. And we do this using a threshold verifiable random function. And for this talk, I won't make much distinctions between unique signatures, verifiable unpredictable functions, and VRFs. We can treat all of them as, very similarly. Okay, let's look at one example of threshold verifiable random functions, or this BLS unique signatures, and it works as follows. It's a unique threshold signature scheme. So we have a set of signers. Each of them will have some signing key. And the signing keys are typically n, t Shami shares of some random secret S. Okay, and we can assume that they have generated this key by running a distributed key generation protocol. And once we have this situation, the threshold signature protocol works as follows. To sign a message, each signer will just take the message, hash it, and raise it to their individual signing key. So it will be simply hash of the message raised to the SI. So each signer will locally do this. This is a local operation. And then they will send this partial signature, this row I, to an untrusted aggregator, which will simply run some public operation, which is Lagrange interpolation in the exponent, to get the unique signature here, row, which will also be the VRF output. Okay, this is some very nice properties. For example, it is non-interactive signing. Everybody needs to do only local computation. It has order 1 partial signatures, and it also has quasi-linear aggregation cost. So this is very efficient, and we can use this to design a randomness beacon within the blockchain. And how do we do this? This is very simple. Once we are running the blockchain, every time we generate a block, we can evaluate the threshold VRF on the hash of the block and use that as our random value. And this is great. We can do this repeatedly. And it addresses all the limitations that I described. That now intuitively what happens is VRF requires T+1 parties because of the threshold property. And also it only needs 1 round of communication. As a result, it gets the same security as the underlying blockchain. And in terms of latency, we only get 1 additional round of latency. This is great. But the question is, are we done? The answer is no. It's no, because we want a weighted VRF. The blockchains that we work with have parties with weights. Specifically, it looks as follows. So we have a set of validators or parties, and each of them will have their individual weights. And these weights are proportional to the amount of token or stake that they control in the blockchain. For example, and the security guarantee we want is the validators of combined weight at most 1/3 are malicious. So if you look at the Aptos blockchain as an example, so as of March 2024, we have 880 million tokens at stake. There are total 129 validators, and also the distributions vary. For example, we have 14 validators with a very high weight of like 15 to 20 million tokens, and also we have a large number of validators with small amount of relatively small amount of tokens. So although these are 880 million tokens, we can do some kind of quantization to round them off, but even after rounding, we get like thousands of weights. Okay? So in this paper, we want to design a weighted verifiable random function that works for this proof of stake blockchain applications, and also for other things. So let's see a naive example of how to design a weighted VRF, and this is using this virtualization technique. And this is very simple, trivial. This is how it works. So let's say we have 4 validators. Each of them have some weights, 1, 3, 2, 3 here. And to each validator, we assign some number of secret shares proportional to their weight. The first validator will get a 1 secret. The second validator has a weight of 3, so it will get 3 signing keys in the BLS signature scheme, and so on. And then to compute the VRF, each of them will compute, take the message and evaluate the VRF locally. The signer 1 will compute row 1, which is 1 VRF output. Signer 3 has weight 3, it has 3 signing keys. So it will use the message to generate 3 VRF outputs, 3 partial VRF outputs, and so on. And then they send this to an untrusted aggregator, which will just run the BLS interpolation algorithm to generate the VRF output. So this works fine. This is a feasible solution, but as you can see, it has issues that the per-party VRF evaluation is proportional to the weight, and also it has an aggregation cost proportional to the total weight, and we need a distributed key generation which is proportional to the total weight. So unfortunately, we don't know how to address all of these issues, but we'll address part of these. Okay, so let's look at how we design our weighted VRF. I won't talk into the details, but I'll just give a high-level idea of what we do. Okay, so let's say we have, again, the signers with the individual weights, and the total weight here is 9, 1, 3, 2, 3. And the first step we do is similar to the virtualization-based approach. So we generate the 9,6 secret sharing. Let's say the secret sharing proportional to the total weight. So we generate 9 shares. But instead of handling the shares to this individual validators, we instead encrypt them. We somehow encrypt them and make the encryptions public. And the way we encrypt them is very critical. So this is what we do. We expect that the first signer will get 1 secret share, so we encrypt the first secret share with an encryption key K1 and derive C1. For the second validator, it's supposed to get 3 shares, so we encrypt all 3 shares, share 2, share 3, and share 4, using a common key K2, and derive the ciphertext C2, C3, C4. And we do the same for everybody. Okay? And then instead of assigning this shares to this validator, we instead assign them this constant size encryption keys that we use to encrypt the shares. Now, to the untrusted aggregator, we give all the ciphertext. The ciphertexts are public, and the untrusted aggregator will get those ciphertexts. Now, to do a VRF evaluation, each validator or signer will take this message and will compute a local partial VRF. He used sigma I to denote here. So this is just a constant output. Signer 2, validator 2 will use compute row 2, and so forth. So each validator uses a constant size key and uses the message to derive a constant size VRF evaluation output, roughly. And then they send this sigma i's to this untrusted aggregator. An untrusted aggregator will do some public operations to carefully expand these 2 components. Specifically, this untrusted aggregator takes the sigma I, which is the output of party I, or validated party 1, and takes the corresponding ciphertext to expand publicly and get the partial VRF output row 1. It will do the same for validator 2. It will take the constant size sigma 2 and the public ciphertext that it has to generate this VRF outputs. And it publicly does this operation, and then we can use this Lagrange interpolation in the exponent to use this row I values proportional to the total weight to get the final VRF output. And if you have seen, this is very similar to the functional encryption that it happens. So we encrypt some message, and then we are outputting some function of the message in a carefully crafted way. Okay? Good. In terms of properties, the per-party VRF evaluation, the VRF output are constant, but as I said, we still have some limitation that the aggregation cost is proportional to the total weight. And we need a distributed key generation, which is proportional to total weight, but we have a lot of optimizations in the paper. We have a new publicly verifiable secret sharing scheme, and also some other tricks to make this tractable, the distributed key generation protocol. So I want to look at some of the results. As I said, this is running in the Aptos blockchain. So, and this is evaluation from the production Aptos blockchain, where, so as I said, we have 880 million total state, but we can do some kind of quantization to keep the total number of weights tractable. And as you can see, the DKG takes a reasonably long amount of time, but the randomness randomness outputs are very fast. It's order of hundreds of milliseconds. And also we have some other consensus level optimization that we did later in the paper, which reduces this randomness beacon latency to like order of 20s millisecond. Okay? But DKGs are longer, but that's reasonable because we need to run this DKG once per every epoch, which is roughly 2 hours in the Aptos blockchain. But I want to say this is a very interesting open problem to address this issue. I also want to show some comparison with how it compares with the VLS virtualization approach using a micro benchmark. And this is using, and this is how it looks. You don't have to really look at the number, but just get a sense of how it compares. So as expected, the evaluation time per party is much better. In our case, we just have to do a constant operation, and in BLS, the cost is proportional to the weight. Same with verification time. We need to do a constant verification. It doesn't grow with the total weight, but in BLS, it grows linearly. And as expected, the VRF size per party is also constant. But we have there are some other parameters where we don't do as well as BLS. Here, both of the, which is the VRF derivation time. Here, both of the parameters are linearly growing, but in our case, we do by pairing operations, and BLS, you just have to do group operations. So we see a little bit more growth. But if we combine everything together, our total aggregation time, the aggregation cost of the aggregator is still lesser than the VLS virtualization. Okay, so this is my last slide. I want to summarize. So we designed a randomness beacon in the weighted setting using a weighted VRF with the constant evaluation cost per party. And we also, in the paper, have a new aggregatable publicly verifiable secret sharing scheme, and also a new distributed key generation protocol. And it's running in production in the Aptos blockchain. And we prove its security assuming this bilinear Diffie-Hellman assumption in the bilinear pairing group. There are some very nice open problems. First is the distributed key generation is still virtualization based. And also the secret key that we get in our VRF is a group element. And also we can, it'll be nice to improve the aggregation cost and the verification cost. And that's all I have.
Thank you very much for the presentation. Any questions? In the meantime, I have a question. So this is based on the bilinear Diffie-Hellman assumption. Is the whole framework reasonably modular so that you can easily port it to, let's say, lattices, or is it very tied to group operations?
We start with a unique signature scheme. With lattices, I don't know whether we have any unique signature scheme, so that'll be the first bottleneck. And this has this functional encryption decryption structure that we want to be able to decrypt in a certain way. I don't really know if lattices will give us those. I still have a minute. I can go slightly show how the actual construction work in the unweighted setting. So let's say these are the Shamir shares that we generate. So how we encrypt is as follows. So we have a group element, and we have the encryption key K1, and the secret share S1. We just put both of them in the exponent. So we get h to the K1 times S1. That is our encryption. It's not a perfectly hiding CCA style encryption, but it's sufficient enough to give us the weighted VRF that we need. And we do the same for everybody. And the VRF evaluation is also very simple. you take the message, and you just hash the message and raise it to 1 over the encryption key that the signer got. Okay? It's also, again, very simple. And to do this VRF derivation, you just take the bilinear pairing of the ciphertext, which is the C1, which is h raised to k1 times S1, and along with the VRF evaluation that the party outputs. So the k and 1 over k cancels out, and we just get this very nice structure, which is very amenable to do this Lagrange interpolation in the exponent.
Okay, thank you.
Yeah, thank you.
Any other questions? Okay, then let's think sort of again. The third talk in the session is about LEAP, a lattice-based OPRF. And it's going to be given by Lena Heimberger.
Yeah, thank you. So this is joint work with Daniel, Ricardo, Omid, Sebastian, and Christian. And I'm going to start with the very large claim that we have, is probably the biggest one, which is that we have an OPRF that is as fast as elliptic curve OPRFs in online computation. That allows us to do an unbalanced set intersection between 60 million and 32,000 items in under a minute online time and 2 minutes overall. And that's because the OPRF operations online are very simple linear operations like bit shifts and additions. Independently of this, because it's not a part of the talk, but I think it's a very nice result, we also have the first modification of the 2-DHGC proof framework for now wrangled OPRFs. So if you want to do now wrangled, that's maybe interesting for you as well. So I'm going to start by talking about what an OPRF actually is. So an OPRF is a two-party protocol between a client and a server, and the client has some input C, and the server has some key K. And the client and the server want to jointly evaluate the pseudorandom function between the key and the input, and then get the output Y, and it's oblivious if only the client gets the output Y and learns nothing else, especially nothing about the server key, and the server learns nothing, especially nothing about the input or the output. And OPRFs are really nice protocols. You can you can use them as a building block in a number of other protocols. If you want a quick intuition, basically anytime you send a hash over the internet, it would be better to use an OPRF. You can use it for something like privacy pass, but also for private set intersection. So, as I said, we want to do an OPRF, but first I'd talk about the PRF we actually wanted to evaluate, and we chose Spring, which is a lattice-based pseudorandom function. It was at FSE 2014. And it's a heuristic PRF based on a learning with roundings problem. It's heuristic because of the small modulus, which may be a proof artifact of the original LWR construction. And actually seems like a reasonable assumption. So Spring has two modes. One of them has a modulus of 257, which, if you know lattice cryptography, is really, really small. But other schemes are also going towards smaller moduli. And also Spring CRT with twice as large modulus of a still very nice 514. So in this work, we focused on Spring BCH. So if you round from 257, you're obviously going to have a bias. And we mitigate this bias by applying a BCH code from 1 over 257 to minus 2 to the 143, I think. And then it's suddenly very manageable. And we focus on this because we only get 64 bits of output, but because we wanted to do really fast private set intersection, we actually figured it was fine. So how does it look? It looks a lot like now wrangled. If you don't know now wrangled, basically we have an initial group element. In our case, it's a polynomial in a lattice, K0, and then we multiply it with the if polynomial if and only if the ith input bit is set. If you now think it's trivial to recover K0 by just sending all zeros over, that's why we have the S here, which is the rounding function. And if we round, it's actually secure. And because we use Spring BCH after rounding, we have to apply the BCH function as well, so S is rounding plus BCH. Okay, so now that we know Spring, let's talk about how to obliviously evaluate Spring. But first, I'm going to show you some optimizations that we're going to need for that. And the first one is that if we do lattice space cryptography, very often it's nice to perform, instead of polynomial multiplication, perform pointwise multiplication, and then apply the inverse NTT. We didn't convert to the NTT because we can already sample in this domain. And in case pointwise multiplication is still too heavy for you, no worries, because you can also just do pointwise addition. And then you have to perform a lookup. We are bit slicing it, but and then you can just compute a subset sum, perform a table lookup, perform the inverse NTT, and perform the rounding, and then you get a really, really fast PRF. So in order to obliviously evaluate, we need primitives for oblivious evaluation. The first one is going to be 1 out of 2 oblivious transfer. Very well-known primitive. The client has an input bit, there is a choice bit, the server has 2 messages. Client can choose between the 2, learns nothing about the other message. Server learns nothing about the choice. And OT is really nice because we can very easily extend it with symmetric operations. So we perform a few OT calls and then can cheaply generate several more. A primitive that's very closely related is Q out of 1 OT, where the client can choose between Q messages. Same guarantees, learns nothing about the other messages, server learns nothing about the choice. And we can build this from logarithmically many OT calls, which is quite nice. And then the third primitive we need is oblivious linear evaluation. So the client, again, has an input, but this time it's an integer. Server also has an integer. And at the end of OLE, the client gets the blinded product, additively blinded product, and the server gets the unblinding terms. And once again, we can construct this generically from logarithmically many OTs. Both for Q out of 1 OT and for OLE, there's also non-generic constructions, but they were less efficient, so we just constructed everything from OT. So back to Spring. We're going to evaluate from the inside out. So first, this is, if you know now wrangled, this is going to look a lot like doing normal now wrangled. For each input bit, the client can choose between a blinding element and a blinded key. And they do this for each input bit. And at the end of the protocol, the client has a blinded subset sum, and the server has K0, which is needed for the final evaluation, and all of them blinding elements. And since we have now done the hardest part of the protocol, we can switch from additive to multiplicative representation by using our lookup or bit slicing evaluation. And now we have our multiplicatively shared elements. And that's a bit annoying when we want to do rounding. So what we do is that we now change the multiplicative sharing to an additive sharing via oblivious linear evaluation. So we take as an input the polynomial coefficients of each shares, and then the server has the unblinding elements, and the client has the additively blinded polynomial. And now we can actually leave the NTT domain and only need to perform the rounding anymore. And we perform the rounding by the server pre-computing all possible rounding results for each of the coefficients. It's only 257 possibilities, so that's actually not that big. And the client can then choose whichever one they have, and then the protocol will be done. Except we said we use Spring BCH, so we need one tiny step, which is that we need random bits to mask the rounding results, so we don't leak anything here, and then also send over the BCH code of the masking, and because BCH is commutative, when we compute the BCH over the rounding results that we got from here, and then XOR it with this BCH, it cancels out, and we got the full evaluation. And that's actually everything we need. But that's a bit expensive, and we're going to get rid of all of these blocks by doing pre-computation. So let's look how much pre-computation we have to do. So for the subset sum, we have to do MOT calls, which is like 128. Then from the Spring parameters, we need the polynomial degree, the modulus, and the logarithm of the modulus. For the oblivious linear relation, we need n log q OTs, and we also need n log q OTs for the rounding. Overall, that's 2,432 OTs, which is a bit too many, so we just use 128 base OTs and extend them then afterwards with whatever method you would like to. And that gives us a really nice online phase that can also now be a bit bigger on the slides. So the client only really has to correct during the online phase what they had as a base OT. So they send over m bits as 16 bytes, and the client sends over m correction polynomials. Then we do some local computation. The client then sends the OLE correction bits, which is n log q bits, and the server sends back the packed OLE corrections. It's not packed in a reference implementation, but that's easy to do. And then we do some more local computation, and for rounding, we need to send again n log q bits on the client side, and the server needs to send q bits, q possible rounding results, and times. So, and then if you have the BCH code, you also need to send 8 additional bytes, but you can send them in the same round. And after you're done, the client has sent 304 bytes, which is pretty nice for doing lattices. And the server has to send 22 kilobytes. And as I said, this is very fast. So for the client, because they only have to send corrections, it's 11 microseconds, which I think could also be faster, but I stopped after I was faster than elliptic curves doing optimizations. And the server has 227 microseconds, which is still faster than elliptic curves. I should put an asterisk on that, because we have more rounds. So it's 6 rounds in total, and in the implementation, if you run it, you're going to see okay, actually, it's a bit longer because of network buffering and because we didn't optimize the network all that much. So pre-computation, it's really your choice of your favorite OT and OT extension protocol. We used simplest OT to illustrate, oh, the world would be nice if we could still use elliptic curves, but then we could also use 2#DH. And then with Kaiba OT, we have a bit higher communication, but we're actually faster, which is nice. And if you do a large number of evaluations, you may want to use something like silent or soft-spoken OT extensions, because you have to compute for a bit longer, but overall, you get a relatively performant protocol, which I think is quite neat. I did say that it's optimized for private set intersection, and I would start with the disclaimer. I don't think that Leap is going to replace the 2#DH for a number of reasons, but the most important one is Leap is not a verifiable OPRF, and I don't think it's going to be, because we have a lot of keys coming from the now wrangled, and that will be really large zero knowledge proofs, and then maybe use something else. So it's great for applications that need many OPRF calls, like private set intersection, where Alice and Bob, or server and client, have 2 differently sized sets. And they just compute an OPRF over all of Alice's set elements. And then Bob sends over the PRF of all of their set elements. And if X and Y match, then Alice can see this locally, and otherwise Bob's PRF outputs absolutely random, and it doesn't matter. These are some comparisons. This is a very fair comparison for other protocols, because you put preprocessing and online phase together. But what I want to illustrate here is that while we still need like 2 seconds, it's significantly better than, for example, isogeny-based protocols, also in terms of communication and computation. And we're actually now in the same ballpark as elliptic curves, somewhat. Yeah. And also to talk about OPRFs in general, Leap is here. There's a number of really cool OPRF results. So it's a very active field doing PQ OPRFs. So Leap is kind of reasonable in between a lot of them. And I think it's going to be really interesting how this turns out. I'm almost out of time, so if you want to talk about OPRFs and want to have this nice table in better resolution, you can have it at my website. And other than that, I hope I could convince you that learning with rounding and OPRFs from it is quite nice. Yeah, and that's it. Thank you.
We have time for questions.
Quick question. You mentioned that you don't think it's likely that you can make it verifiable. Can you say a little bit more about that?
So there are two things that are painful to make it verifiable. I'll just go to the back to the protocol. The first one is we have a really large number of keys. Like, maybe it is. I was actually thinking about it yesterday, and I keep thinking it's easy. But I think what's really annoying, actually, maybe I better go to the online phase. So we have so many rounds, and it's, at least for me, but maybe I missed a really nice work, it's difficult to prove between the set representations that we still work with the same polynomials. And because we have so many rounds, I think it's going to be really involved, and just, in my opinion, also really nice other constructions that may be able to do it more efficiently, but it would be nice to look at it.
You maybe partially answered it, but have you considered applications to PAIC, like opaque or PPSS? Is it the round complexity which is a bottleneck?
So for opaque, people really want to use verifiable OPRFs. If you have some trust assumptions in there that you're okay with semi-honest, then yes, I think it would be possible.
So the round complexity is not going to be an issue, because usually for these things they want like 2 or 3 rounds or something. So.
I mean, it depends kind of what you want to do. Leap is significantly faster than blind signatures right now, because it also has lower guarantees. If it's just the rounds, then maybe because the computation is so fast, it's a trade-off.
And sorry, maybe another quick one. And you mentioned that you have UC security in the OPRF setting, so it would play, because here this opaque, I think they need like some UC security. So
yeah, we have a really nice UC proof by primarily Ricardo. Yeah, so he can tell you more about that.
Okay, any other questions? If not, then let's thank Lena again.